In the early days of wireless networking, our primary goal was simply to establish a reliable connection. But as our digital lives have expanded, we have moved into an era where the sheer volume of data being moved across the air is staggering. We are no longer just sending simple messages. We are streaming high-definition video, managing real-time cloud computing, and connecting dozens of devices simultaneously. To keep up with these massive bandwidth demands, wireless technology has had to undergo a fundamental shift in how it operates. For a long time, communication relied heavily on single-link constraints where a device essentially waited its turn to use a specific channel. While effective for basic tasks, this creates a bottleneck where dozens of high-demand devices are fighting for the same space. To break through this limit, modern architecture have moved toward extremely high throughput models. This isn't just about making the radio faster. It's about changing the entire way data is organized and moved. The secret to this evolution lies in the deep integration of the physical layer and the media access control layer. The physical layer handles the raw radio waves, managing the complex modulation and signal processing that turns electricity into data. At the same time, the media access control layer acts as the conductor, managing how every device on the network accesses the airwaves to avoid collisions. By tightening the link between these two layers, the system can do much more than just transmit a signal. It can now utilize much wider channels and coordinate complex multi-user interactions with incredible precision. This allows the network to act less like a single lane of traffic and more like a massive multi-lane highway, delivering massive throughput and low latency even when the environment is crowded. In a traditional wireless network, a device typically operates on a single connection at a time. When we think of a standard station, we imagine a device tied to one specific frequency or one particular channel. If that channel becomes crowded or experiences interference, the device has to wait for the airwaves to clear before it can send or receive more data. This creates a bottleneck because the device is essentially locked into a single lane of traffic. A multi-link device, or MLD, changes this fundamental approach by breaking that single link limitation. Instead of being restricted to one frequency, an MLD can manage multiple simultaneous radio links across different bands or channels at the same exact time. Imagine a highway where, instead of being stuck in one lane, a vehicle can seamlessly shift between multiple lanes or even use two different paths at once to reach its destination faster. To make this coordination possible without chaos, the architecture uses a split management structure. At the heart of the device is a centralized MAC sublayer. This is the brain of the operation. This higher-level management layer handles the heavy lifting of coordination, making intelligent decisions about where the data should go and how to distribute it across the available links. Below the central brain, the architecture maintains individual links that handle the specific low-level operations required for each radio frequency. By separating the high-level logic from the individual radio links, the device can steer data dynamically. If one band becomes congested, the central management can instantly shift the load to another band without dropping the connection. This sophisticated architecture allows for much more efficient use of the available spectrum, providing a more stable and high-performance connection by treating multiple frequencies as a single unified resource. Imagine a device that isn't limited to just one frequency or one lane of communication. Instead of being tied to a single connection, multi-link operation allows a device to treat multiple wireless links as a single, unified, logical connection. This framework changes how devices interact with the network by allowing them to spread their data across different channels simultaneously, drastically increasing efficiency and reliability. How a device actually manages these multiple links depends heavily on its internal hardware capabilities, specifically regarding how it handles transmitting and receiving at the same time. In a high-performance mode known as simultaneous transmit and receive, or STR, a device is capable of sending data on one link while simultaneously receiving data on another. Because the device can effectively isolate these signals, there is no internal interference, allowing for truly parallel communication. However, not every device has the hardware complexity required for that level of isolation. In a mode called non-simultaneous transmit and receive, or NSTR, the device faces a challenge where transmitting on one link might drown out the ability to listen on another. In this scenario, the device can perform both actions at the same exact moment on different links without causing self-interference. Instead, it must carefully coordinate its timing, alternating its transmissions and receptions to ensure the signal remains clear. Beyond just managing these two modes, this framework provides the intelligence to adapt to the world around us. It allows for dynamic link management, meaning a device doesn't have to stick to a rigid setup. As environmental conditions change, perhaps a new source of interference appears, or a user moves farther away, the device can enable new links, disable underperforming ones, or reconfigure its entire connection on the fly. This constant real-time adjustment ensures the connection remains as stable and as fast as possible, regardless of the changing surroundings. When we look at how data actually moves through the air, we have to consider how to use the available radio spectrum as effectively as possible. Instead of treating a wide frequency channel as one single massive pipe that can only be used by one person at a time, the physical layer breaks that pipe down into much smaller, more manageable pieces. This is achieved through a technique called orthogonal frequency division multiplexing, or OFDM. By using OFDM, we can divide a wide channel into a grid of tiny subcarriers. We then group these subcarriers into specific building blocks known as resource units. Think of these resource units as individual packets of spectrum that can be assigned to different users simultaneously. These units aren't all the same size. They come in various granularities, ranging from very small allocations of 26 tones to much larger blocks of 242 tones or more. This flexibility allows the system to be incredibly surgical. If a device only needs to send a tiny bit of data, like a simple text message, it can be assigned a small resource unit, leaving the rest of the spectrum free for someone else. As our wireless environments become more demanding, we need even more capacity. This is where multi-resource units, or MRUs, come into play. An MRU allows the system to take several of those smaller resource units and group them together into a larger, contiguous block of spectrum. This is vital for high-demand users who need to download massive files or stream high-resolution video. This ability to scale from tiny individual units up to large, combined blocks is what makes it possible to manage incredibly wide channels such as those spanning 320 MHz. By managing spectrum at this granular level, the system ensures that every hertz of available frequency is working as hard as it can. Every wireless transmission begins with a preamble. Think of a preamble as a specialized sequence of signals that acts like a handshake, telling every receiver in the area exactly how to interpret the incoming data stream. Without this initial signal, a device wouldn't know the timing, the frequency, or the method required to decode the actual information that follows. In high-efficiency transmissions, this preamble is built using a layered structure. This layering is a clever way to manage coexistence. The first layer consists of legacy components that are recognizable by older generations of hardware. By starting with these familiar signals, we ensure that even older devices can detect that a transmission is currently occupying the airwaves. This prevents them from transmitting at the same time and causing interference, allowing the network to maintain order across different levels of technology. Once the older devices have identified the transmission, the signal moves into specialized high-efficiency layers. The first of these is the universal signal, or U-SIG. This layer provides the essential high-level parameters needed for the transmission to function. It essentially sets the stage, communicating fundamental details about how the signal is structured so that modern receivers can prepare themselves for the incoming data. Following the universal information is the EHT-SIG. While the previous layer was broad and general, the EHT-SIG is highly specific. This layer contains the targeted instructions necessary for data delivery to particular users. This is what makes complex multi-user transmissions possible. Because this part of the signal can carry user-specific information, the network can communicate with multiple devices simultaneously, directing different parts of the data stream to the exact devices meant to receive them. This layered approach transforms a simple burst of radio waves into a sophisticated, organized conversation. To achieve extremely high throughput in modern wireless communication, we have to find ways to pack more information into the same amount of spectrum. One of the primary ways to do this is through advanced modulation and coding schemes. Think of modulation as the way we shape a radio wave to represent data. When we use higher order modulation, we are essentially increasing the density of the data. Instead of using simple patterns to represent a few bits, we use much more complex patterns that allow us to pack many more bits into every single symbol transmitted. This significantly boosts our data rates, but there is a fundamental trade-off involved. As we increase the density, the signals become much more sensitive to interference. Because the difference between these complex patterns are so small, even a little bit of background noise can cause the receiver to misinterpret one pattern for another. To prevent this from breaking the connection, we use sophisticated error correction methods such as low-density parity check codes. These are mathematical frameworks that add a layer of intelligent redundancy to the data stream. If some bits get corrupted by noise during transmission, these codes allow the receiver to perform complex calculations to reconstruct the original, perfect data without needing a retransmission. Even with strong error correction, certain environments are so challenging that we need an extra layer of protection. This is where techniques like dual carrier modulation come in. Rather than sending all the information on a single frequency, we can split the data and transmit it across two different carriers. By spreading the information across different parts of the spectrum, we gain a massive boost in reliability. If one frequency experiences a sudden fade or interference, the information traveling on the second carrier can still bridge the gap, ensuring a stable and robust connection even when the environment is working against us. In any wireless network, devices constantly compete for the same shared airways. If every device tried to transmit at the exact same time, the signals would collide, resulting in lost data and constant retransmissions. To prevent this chaos, the medium access control layer acts as a traffic controller, deciding exactly when a device is allowed to speak. The most common way this is handled is through a contention-based approach. Think of this like a polite conversation in a crowded room. When a device has data to send, it doesn't just start talking. It first listens to see if the channel is busy. If the channel is clear, the device initiates a process called Enhanced Distribution Channel Access. This involves a back-off procedure where the device picks a random waiting period. The device counts down this timer, and only when it reaches 0 does it gain permission to transmit. If another device starts talking during this countdown, the timer pauses and waits for the airways to clear again. This randomization is critical because it prevents multiple devices from all jumping onto the frequency the very instant a transmission ends. To make sure one device doesn't hog the entire channel and starve others of bandwidth, the system imposes time limits on how long a single transmission burst can last. This is known as a transmit opportunity limit. Once a device has used up its allotted time, it must step back and let the contention process happen again, ensuring everyone gets a fair turn. While the contention works well for individual devices, modern networks often need much higher efficiency. For highly coordinated scenarios, the system moves away from competition and toward a scheduled approach called triggered access. In this mode, a central access point takes full control. It sends out a specific trigger frame that tells multiple devices exactly when to transmit and which frequencies to use. This allows many devices to communicate simultaneously in a perfectly timed, synchronized dance, maximizing the total capacity of the network. In modern high-efficiency wireless networks, the ability to communicate with multiple devices at the exact same time is what allows a network to stay fast even as more devices join. Instead of forcing every device to wait in a queue for its turn to speak, we can use multi-user operations to serve several users simultaneously within a single transmission window. This is achieved through two distinct but complementary techniques: spatial multiplexing and frequency division. First, we have multi-user MIMO. This technique uses spatial diversity to create separate paths through the air. By leveraging multiple antennas, an access point can direct different data streams to different users at the same time, all while using the same frequency channel. It is essentially like having multiple dedicated lanes of traffic flowing in different directions simultaneously, allowing more data to reach more people without increasing the amount of spectrum used. The second technique is orthogonal frequency division multiple access, or OFDMA. While MIMO works with spatial streams, OFDMA works by dividing the available frequency channel into smaller, manageable pieces called resource units. Think of the wireless channel as a large highway. Instead of sending one giant truck down the lane, we divide that highway into several smaller lanes. We can then assign a specific resource unit to each device, allowing them to transmit their data in parallel on their own dedicated frequency segments. Coordination is the key to making this work, especially when devices need to send data back to the access point. To manage uplink communications, the access point acts as a conductor. It sends out a trigger frame that tells specific devices exactly which resources to use and when to start transmitting. This ensures that when multiple devices respond, they do so in perfect synchronization, preventing them from interfering with one another and turning a chaotic scramble into an organized and efficient conversation. Imagine you're trying to ship a large number of small items through a delivery service. If you send every single item in its own individual box, you end up spending more money on packaging, labels, and shipping fees than you do on the items themselves. In high-speed wireless communication, we face a very similar problem. When we transmit small packets of data individually, each one requires a significant amount of overhead, such as headers and specialized signaling, to make sure it reaches its destination correctly. If the overhead is larger than the actual data being sent, the connection becomes incredibly inefficient, wasting precious airtime. To solve this, we use a technique called data aggregation. Instead of sending packets one by one, we bundle them together to maximize the amount of real information moving across the link. There are two primary ways we do this. First, we can use a method that wraps multiple small data units into a single, larger MAC frame. This is known as A-MSDU aggregation. It essentially acts like putting several small envelopes inside one larger, single envelope before they even leave the local processing stage. The second method is A-MPDU aggregation, which takes entirely separate MAC frames and bundles them into one single physical transmission. While the first method combines the contents, the second method bundles the frames themselves into one massive burst of radio energy. By using these techniques, we significantly increase the ratio of actual data to overhead, which pushes our effective throughput much higher. However, this isn't just about packing as much as possible. The system has to carefully manage length limits and spacing to ensure everything fits within the allocated time and frequency resources. If a bundle is slightly too short for the required transmission window, we use padding to fill the gap, ensuring the timing remains precise and the transmission is as efficient as possible. For mobile devices, battery life is everything. In a typical wireless environment, a device often spends a significant amount of energy just listening to the airwaves, waiting to see if there is data waiting for it. This constant state of readiness is a massive drain on power. To solve this, we use a mechanism called target wait time. Instead of a device constantly monitoring the network, target wait time allows an access point and a device to negotiate specific, agreed upon moments when the device will wake up to communicate. Between these scheduled windows, the device can enter a deep sleep state, turning off its radio components and preserving its battery. It essentially knows exactly when it needs to be awake so it doesn't waste energy listening to the silence. There are two main ways this scheduling happens. In an individual arrangement, a specific device can negotiate its own unique wake-up schedule with the access point, tailored to its own specific needs and traffic patterns. Alternatively, an access point can use a broadcast approach where it announces a general schedule that multiple devices can follow. Beyond just saving power, this scheduling serves a second, equally important purpose. It manages congestion. In a busy network where many devices are competing for the same airwaves, they often collude or wait in long queues, which creates overhead and inefficiency. By spreading out the transmission times throughout the scheduled windows, we reduce contention. Because devices aren't all trying to talk at the exact same time, the network becomes more organized. We move away from a chaotic environment of constant competition and toward a streamlined system where communication is predictable, efficient, and extremely energy conscious. When you connect a device to a wireless network, security isn't just an afterthought or an extra layer added on top. Instead, it is built directly into the foundation of the connection itself through a process called a robust security network association. Think of this as establishing a secure, encrypted tunnel before a single bit of sensitive data is ever allowed to pass through. Before this tunnel is even built, the devices involved have to prove they belong there through a rigorous authentication process. A modern and highly effective way to handle this is through a method called simultaneous authentication of equals. This approach is designed to provide strong, password-based security that is much more resilient than other older methods. Unlike traditional systems where one side acts as a master and the other as a client, this method treats both the devices and the access point as equals during the handshake. This symmetry ensures that neither side is blindly trusting the other. To make this work, the system relies on advanced mathematics, specifically password-based elliptic curve cryptography. It uses complex structures known as finite cycle groups to perform calculations that are easy to execute in one direction but incredibly difficult for an attacker to reverse. By using these elliptical curves, the devices can perform a sophisticated exchange that proves they both know the correct password without actually sending the password itself over the air. This entire exchange is managed through a series of precise handshakes and state machines. These steps act like a choreographed dance, where each movement must be verified before the next one can occur. This ensures that the station and the access point are exactly who they claim to be. Only after this mathematical proof is complete can the system generate the unique encryption keys needed to protect your data, ensuring the connection is both private and authenticated from the very first moment. Once a device has successfully authenticated to a network, the focus shifts from providing identity to ensuring privacy. At this stage, the network must guarantee that every bit of data traveling through the air remains confidential and protected from eavesdropping. This is achieved through robust encryption protocols. You might encounter CCMP, which combines counter mode for privacy with a block cipher-based message authentication code to ensure data integrity, or the faster, more modern GCMP, which uses GALVA or counter mode to provide both encryption and authentication in a single efficient process. To make this encryption work effectively without exposing the most sensitive credentials, the system relies on a strict key hierarchy. Instead of using a single master key to encrypt every packet, the system derives multiple specialized keys for specific tasks. For example, when a device sends private one-to-one communication to the access point, it uses a pairwise transient key, often called the PTK. This key is unique to that specific connection. However, when the network needs to send data to everyone at once, such as a broadcast or a multicast message, it uses a group temporal key or GTK. This allows a single key to be shared among all authorized members of the network for group traffic. Establishing these individual session keys requires a carefully coordinated process known as the four-way handshake. During this exchange, the device and the access point use specific management frames to prove they both possess the necessary credentials without actually sending those credentials over the air. This process allows them to derive the unique PTK and the GTK dynamically. By using this hierarchical approach and refreshing keys through the handshake, the system ensures that even if a single session key is somehow compromised, the rest of the network and the original master credentials remain secure. Every wireless device has a unique fingerprint called a MAC address. This address is intended to help networks direct data to the right hardware, but it creates a significant privacy problem. Because this identifier is normally static and permanent, it acts like a digital license plate. If you move from a coffee shop to another airport to a shopping mall, any observer with the right equipment can log that specific address and then reconstruct a map of your movements. This allows third parties to build a detailed profile of your habits and locations without your knowledge. To combat this, we use MAC privacy enhancements that decouple your physical hardware from your network identity. Instead of broadcasting your true permanent address, your device can use an identifiable random MAC address or a rotating device ID. Think of this like a burner phone number that changes every few days. When your device connects to a network, it presents a temporary identifier that looks and acts like a real MAC address, allowing the network to manage your connections, but it doesn't reveal who you actually are. By periodically changing these identifiers, your device breaks the digital trail. An observer might see a device present itself at a mall at noon and then see a different random address at the airport an hour later. To them, these appear to be two completely different people rather than the same individual moving through the space. This technology mitigates tracking by making it computationally difficult to link these disparate sessions back to a single user. It strikes a vital balance. Your device remains functional and easy for authorized networks to manage, while your physical movements remain anonymous to unauthorized observers. Imagine you're walking through a large office building or a campus while on a high quality video call. As you move from one area to another, your device needs to switch its connection from one access point to the next. In a traditional setup, this switch can cause a noticeable hiccup. The device has to break its current connection, find a new access point, and then go through the entire process of proving who it is and exchanging security keys. This delay, known as handoff latency, is often long enough to freeze a video stream or drop a voice call entirely. To prevent this, we use fast transition protocols to enable seamless roaming. The core idea is to move the heavy lifting of the connection process to the background, so the actual switch happens almost instantly. Instead of waiting until you have already moved to the new access point to start negotiating security, your device begins preparing for the move while it is still communicating with the current one. This allows the device to pre-authenticate with the next access point before it ever leaves the range of the first. There are two primary ways this preparation happens. In an over-the-air transition, the device communicates directly with the new access point using radio signals to handle the handshake. In an over-the-distribution system transition, the device uses its current connection to send the necessary authentication request through the wired network to the target access point. By pre-calculating security keys and handling the authentication ahead of time, the technology ensures that when physical handoff occurs, the new connection is already established and ready to go. This minimizes the time the device spends disconnected, making the transition invisible to the user and the applications they are using. Imagine you are in a crowded coffee shop or a busy office building. In these environments, dozens of wireless networks are all fighting for the same airwaves. This creates a massive problem with the co-channel interference. Normally, a wireless device listens to the air before it speaks. If it hears any signal on its channel, it waits its turn to avoid causing a collision. While this prevents errors, this creates a huge bottleneck. In a dense area, devices spend more time waiting for silence than they do actually transmitting data, which causes the entire network to slow down. To solve this, we use a concept called spatial reuse. The goal is to allow multiple devices to transmit at the same time on the same channel, even if they can hear each other, provided the interference stays within a manageable level. We achieve this by using intelligent preamble detection thresholds. Instead of treating every single signal on a channel as a reason to stop talking, a device can now analyze the incoming signal from a neighboring network. If the detected signal is weak enough, meaning it's coming from a distant network that is far enough away not to disrupt the local communication, the device realizes it can safely ignore that signal and proceed with its own transmission. By adjusting these sensitivity thresholds, we effectively shrink the footprint of what a device considers busy airtime. This allows overlapping networks to coexist much more efficiently. Rather than one massive queue where everyone waits for one person to finish, we create multiple simultaneous lanes of communication. This significantly increases the total capacity of the wireless environment, allowing more devices to stay connected and productive even in the most crowded spaces. To maintain high-speed, reliable connections, a wireless network cannot simply set a frequency and forget about it. The radio environment is constantly shifting, filled with unpredictable interference and new devices entering the space. Because of this, the system must act like an intelligent observer, continuously monitoring the airwaves to ensure that the links connecting devices remain stable and performant. One of the most critical parts of this monitoring is managing shared spectrum. Certain frequency bands are also used by radar systems, such as a weather radar or a military installation. To prevent interference, the network uses dynamic frequency selection. This means the system is always listening for specific radar signatures. If it detects a radar pulse, it must immediately recognize that the channel is no longer safe to use, vacate that frequency, and move the network traffic elsewhere to avoid disrupting vital services. Beyond avoiding radar, the system is constantly performing radio measurements to understand the overall health of the spectrum. Every connected device acts as a sensor, gathering data on the environment. These devices track things like signal strength, the current load on a specific channel, and noise histograms, which show how much interference is present across different levels of intensity. This data is then compiled into reports that give the network a clear picture of where the congestion is happening. When this intelligence identifies a problem, perhaps a channel has become too noisy or is overcrowded with other devices, the network can make a proactive decision to switch channels. By moving the connection to a cleaner, more available frequency before the current one fails, the system ensures that high throughput links stay seamless. This continuous cycle of measuring, reporting, and switching is what allows a network to stay fast and reliable even in a crowded and changing radio landscape.